start the second round. We're running a little bit late, so this next break will be very short. So I think Tom does not need an introduction. If you all attended the debate, you already got a very good introduction from Manish. Just to recap very shortly, Tom works as an assistant professor in the Department of Linguistics at Yale, and he's done a lot of interesting work, where one of his works was really highlighted during the debate, his work on embers of auto-regressive learning, and I think we'll emphasize more on the points that he made already in the debate of this talk. We're very excited to hear from you. Thank you so much.
Great. Yeah, thanks so much for having me here. I've been really enjoying seeing the broad range of perspectives on generalization, even in the short time since I arrived. So the broad question that is motivating this talk is, how can we understand what abilities a given AI system has? And of course, this question is important for a lot of reasons. As AI becomes more and more widely adopted, it's important to know what its strengths and limitations are, so we know when we can trust it and when we can't. And it's also scientifically interesting so that we can know which types of training techniques or architectural choices are sufficient to impart particular abilities. And the very standard answer in artificial intelligence is you develop some test for the ability in question and then see how the AI system performs on it. And so this is a very natural thing to do, but there are some important problems with at least the most straightforward ways of doing this. So I think the problems are well illustrated by clever Hans, who was a horse who lived around 100 years ago in Germany, who was famous for answering questions about math. So you would say, Hans, what is 7 plus 5? And then he would tap the ground 12 times with his hoof. And it wasn't just math. He was also able to answer questions about music or naming objects. So you could say, Hans, name the object that this lady is holding. And then he would say she was holding an umbrella. He would tap out first 21, because U is the 21st letter in the alphabet, then 13 for M, etc., spelling out umbrella. But upon closer inspection, a psychologist named Funkst analyzed exactly what clever Hans was doing and figured out that he was not actually able to do math. Instead, he was just reading the body language of his handler. So when you asked him a question, he would just start tapping the ground. And once he got close to the right answer, the humans in the audience would unintentionally tense up a little bit, and he would use that as his cue to stop. So clever Hans was very clever. It's far from trivial to read the body language of another species, but he wasn't clever in the way that we thought. He didn't actually know math. So the psychologist Funkst has this triumphant conclusion in his write-up of these analyses. I therefore repeat, Hans can neither read, count, nor make calculations. He knows nothing of coins or cards, calendars or clocks, nor can he respond by tapping or otherwise to a number spoken to him but a moment before. Finally, he has not a trace of musical ability. And by the way, as a side note, Hans really did not like this guy because Hans really liked answering these questions and getting treats for getting them right. And then this annoying psychologist came in and messed up his good gig that he had going there. Oh, I guess it's hard to know for sure if he didn't like, but yeah, the behavior was consistent with him not liking it. So the takeaway from clever Hans is that a system that appears intelligent might not actually be intelligent, or at least not in the ways that we think, because any given test could be gamed using some superficial heuristics. So the question then is, how can we distinguish whether some system is using some deeper abstractions as opposed to shallow heuristics? And at least one answer is to analyze systems through the lens of generalization. So that is, don't just have a test for this ability where you see how well it performs on this test. Rather, you can still have a test, but the nature of the test should be crucially informed by what the system has seen during its training phase, so that you make sure that the items you're testing it on require generalization of the sort that these abstractions should be able to support. So the assumption here is that more abstract rules will generalize robustly, but these, for example, will generalize out a distribution, whereas more shallow heuristics will not. So the idea then is to understand what abilities AI systems have. We should analyze how their abilities generalize beyond their training data. And in a lot of ways, this sounds like just the most obvious thing ever to say, because it's, of course, machine learning 101, that you should have a training test split. But in the current era of artificial intelligence, this really this idea, even though it may seem obvious, is really not observed. The standard paradigm is just to have some benchmark that you use across all models, agnostic to what they were trained on. And in many cases, there is actually a pretty solid chance that a lot of those test items were in the training data. Even when people do have this perspective in mind, I think often what happens is just kind of eyeballing the examples and saying, it seems unlikely that this example would have been in the training set. But we do need to be careful with that sort of assumption because the sheer scale of current training sets is absolutely enormous. So the scale kind of just breaks our intuitions about what sorts of examples will or will not have been illustrated. So it's not really safe to assume that something will be qualitatively novel to the system. We ideally really need to check whether it actually appears in that training set. So there are a lot of anecdotal examples that kind of go viral on Twitter, for example, showing cases where LLMs seem pretty intelligent, but actually might just be copying from their training data. So here's one example of a sort of brain teaser. So the brain teaser goes, there's a one-story house where everything is pink. The windows are pink, the floors are pink, the walls are pink, everything is pink. What color are the stairs? Any takers?
Red.
Not red. Yeah, what stairs is the right answer because it's a one-story house. So the answer is there are no stairs in a one-story house. And ChatGPT got this answer right, which seems very impressive. Yeah, this is at least the canonical answer, but yeah. And so it seems pretty impressive because it saw through the trick and it recognized what it means to be a one-story house. But the problem is this is a classic trick question, so it appears many times on the internet, and therefore it's quite likely that it appeared in the training set. So it's possible that ChatGPT is getting the answer right, but for the wrong reasons, just via memorization. And the way we can check that is by perturbing the example in a way where memorization would no longer get you the right answer. So here you can ask, there is a two-story house where everything is pink. The windows are pink, the floors are pink, the walls are pink, everything is pink. What color are the stairs? And now what ChatGPT says is, the house doesn't have stairs because it is a two-story house. So this is pretty clear evidence that in the previous case, it was getting the right answer through something more like memorization. And then this does not generalize robustly once you change the assumptions.
Is this the same section or a new section?
A new session. Yeah, but good question. Yeah, because that can definitely mess up this sort of thing. Yeah. But so this is anecdotal. So I'll be presenting two more systematic case studies, one based on linguistic structure, syntax, and then the other based on algorithmic reasoning, just to try to get more of an empirical sense of to what extent are the abilities of large language models driven by memorization versus more abstract generalization. So this first case study is about linguistic structure, where this is dealing with really the bread and butter ability of large language models, which is text generation. So you give them a prompt, like once upon a time, and then they can continue this text using next word prediction. So GPT-2 continues this prompt as, the world was a place of great beauty and great danger. And so large language models, even ones that aren't that large, like GPT-2, can generate very fluent, coherent, grammatical passages of text. And so this would be consistent with having learned the types of rules that govern linguistic structure and sentence structure, but it's also possible that GPT-2 is just repeating sentences it has memorized because its training set is absolutely enormous. For all we know, that exact continuation that it wrote might have been present in the training set. So in this paper with Paul Smunsky, Tal Linzen, John Fengao, and Asla Chilik-Yilmaz, we just tried to disentangle these two possibilities by generating a whole bunch of text from GPT-2 and then checking it against the training data to see to what extent was this text novel or duplicated from the training set. And so the way we did this was, first we considered n-gram novelty, where an n-gram is a chunk of n words. So for each value of n, we found the proportion of n-grams that were novel. So for example, if n equals 3, we would look at each chunk of 3 words, like the world was a place of, etc. And for each one of these, we just checked whether that same chunk of 3 words appeared in the training set for GPT-2. So this was a benefit of having collaborators at Microsoft who were able to get us access to the training set. Typically, it's not publicly available. And then for each value of n, we just got the proportion of n-grams of that size that were novel. And so here's what we found. The x-axis shows the size of the n-gram, And then the y-axis shows the proportion of those n-grams that are novel. So the solid blue line is this language model GPT-2, and then the dotted red line is just a baseline, which is the test set for the particular corpus that GPT-2 was trained on. So that gives you a sense of the amount of copying that you would expect if it were just purely, perfectly matching the distribution and the relationship between the training set and the test set. And now, when the values of n are pretty small, like 2 or 3, GPT-2's generated text is a bit less novel than the baseline. So for 3 grams, 9% of them are novel in the generated text, whereas in the baseline, it's 14%. But once you get to larger values, it actually becomes more novel than the baseline. So once you get up to n equals 10, that is chunks of 10 words, 93% of the 10-word chunks produced by GPT-2 are novel. That is, they did not appear in the training set, whereas on the baseline, it's 84%. And 10-word chunks are really not that big. Most sentences are longer than that. So it's pretty clear from this that GPT-2 is not simply copying sentences that it has seen before. It is recombining components in very novel ways that do a pretty good job of matching that baseline distribution of the actual training corpus. Now you might ask, okay, so it might not be, oh, sorry, was that a question? Yeah.
When you say proportions of n-grams that are novel, is that n-grams that do not appear ever in the training set? Or like what portion of 2 grams, like of even the possible 2 grams, like are covered in the training set?
Yeah, so this is of the 2 grams that GPT-2 generated, what proportion did not appear in the training set?
Even ones. Okay.
Even ones. Yeah, even ones. Yes, yes. Yeah. And so this shows that GPT-2 is not just copying sentences word for word, but there still are other potentially relatively shallow strategies it could use that would yield that type of novelty despite still not being particularly abstract. So one type of more shallow thing it could do is just be memorizing sentence templates, sort of like Mad Libs, and then filling in the blanks. A template like the noun, verb, the noun, where it just picks some nouns and some verb to fill in those slots. But we can also rule out this possibility. So the way we did this was by measuring what proportion of generated sentences had a novel syntactic structure. And so the way we operationalize this is we use a parser just to get the syntactic structure for every sentence in the training set, which took quite a lot of parsing, and also in the generated text. So the syntactic structure can be represented with a tree like this. And then we just ignored the actual words in the sentence to just get the syntactic structure, like the part of speech of the words, and then the types of phrases that you get, like noun phrase or verb phrase. And so this type of thing, the syntax tree minus the words that are on the leaves of the tree, this is what we mean by the syntactic structure. And a very large proportion, 63% of the generated sentences have a syntactic structure operationalized in this way that never appeared with any sentence in the training set at all. So this rules out the possibility that GPT-2 is just memorizing a template like this. It has to have some deeper compositional process to combine phrases in novel ways. Then just to give a few kind of fun, more anecdotal results. So in addition to having novel sentence structures, GPT-2 also occasionally produces individual words that are novel. And this is possible because its tokens are subword units, so it can combine subword units in novel ways. So novel words like IKEA-ness, Smurf-verse, Brazilianisms, non-neotropical. And the thing that I found especially impressive here is that when it produces these novel words, it also uses them in appropriate contexts where they can be used grammatically. So one example of this is here the word Sirot's is novel. So the training set includes the name Sirot, just the singular name, a person's last name, but it does not include the pluralized form Sirot's. And so here GPT-2 correctly pluralized it to form Sirot's, and that part might not be that impressive because making the plural just means adding the S at the end. But what is impressive is that it also displays the appropriate consequences of that plurality elsewhere in the sentence. So it correctly uses a plural verb, were, as well as a plural pronoun, there. And even the fact that it says the Sirot's, having the word the is something you cannot do with a singular name, like you can't refer to someone as the Sirot, but with a plural name, when you're talking about a family, then you can say the Sirot's. Okay, so yeah, okay. This being like novel individual words. It's very, very rare. Yeah, so this would, I guess, correspond to the 1 gram case in this graph, which, is indistinguishable from 0 on the graph. But yeah, so it's something like, 1/100% or something. Yes, yeah, so it's a, yeah, so we were looking at several different models, some of which were word level and some of which were subword level. So in order to make it more consistent across models, we used word level tokenization. But a weird side effect is that for the subword models, it has this effect. Although it does also mean we can look for the novel individual words, which is just kind of fun. So the basic takeaway here is that when it comes to linguistic structure, whether it be sentence structure or word structure, GPT-2 seems to have done a very good job of learning the structure in at least a reasonably abstract way, a way that cannot be explained away as simple memorization or copying. Now, in the second case study, I'll be turning to some algorithmic reasoning tasks. Now, this does run up against one major challenge. So I think I said earlier was that ideally we should be looking at what the large language model does and comparing it to the training data. But there are some major obstacles in the way of actually comparing what the LLM does to its training data. So the first obstacle is just that the training data sets are getting very large. So GPT-2 is not that large of a language model, or its training set is not that large. But even then, when we were running those analyses in the previous part, it took around 3 days to iterate over the training set in the ways we needed to do to check for whether these n-gram chunks were novel or not. And since GPT-2, more recent models have scaled up orders of magnitude more in the amount of training data. So, I mean, we don't actually know exactly how much training data there are in some of the recent models, but it's quite plausible that it's 100 times more than GPT-2 had. So it starts to get very intractable to even just iterate over the training set to check whether something is novel or not. And then the other big obstacle is that many large language models are trained on proprietary data, which means we just don't have access to the training set at all. So it kind of, I guess, doesn't even matter whether it's tractable or not to iterate over it because we don't have it to iterate over. So in this part of the talk, what we'll instead be using is proxies. So what we do is we take some other corpus that we believe is at least reasonably representative of the training data of the large language model, such as some other corpus of internet text, and then figure out the frequency of the type of example we're interested in that proxy, and make the assumption that frequency within the proxy will be at least pretty well correlated with frequency within the actual training set, so that we can then test whether LLMs are doing better on the more frequent or higher probability types of cases than the less frequent or rarer types of cases. Yeah, so this is from the papers I talked about a bit this morning as well, co-authored with Shunyu Yao, Dan Friedman, Matt Hardy, Tom Griffiths, and Akshara Prabhakar. So the basic prediction here is that LLMs will perform better when the correct answer is a high probability string than when it is a low probability string. Or so this would at least be the prediction, assuming that for the types of algorithmic tasks I'll look at, they are learning it in not a fully abstract generalizable way, but rather in a way that is more closely tied to the statistics of the training data. And so as a first example of getting to this, I'll be using a fairly contrived task called article swapping. So it is contrived, but I think it's useful for getting at some of these points. So in this task, the model is given a sequence of words, like in box the, there was key A, and then it's told to swap each article with the word that comes before it, where an article is the word a, an, or the. So in this case, there are two articles, the word the and the word a. If we swap them with the word before, we get in the box, there was a key. And now just to start with some anecdotal evidence, here's a case. So the input is, it does not specify time a limit for registration the procedures. So the correct answer is to swap a with time and the with registration to get it does not specify a time limit for the registration procedures. So here the correct answer is a grammatical plausible sentence. And therefore, it's reasonably high probability when you feed this into a language model and get its probability. And GPT-4 gets this output exactly right. But now here's another case where the correct answer is complete gibberish. The correct answer here is it few with, it too lying, the take get, a jest hands, would kinds. It's hard to even read it because it's just complete nonsense. And now GPT-4 gets the answer wrong. And I think it's instructive to take a look at what GPT-4 actually produces here. What it says is, it flew with a few kinds to take the lying just to get the hands. So you can really see how GPT-4 is kind of pushing this output in the direction of being higher probability or more plausible. For example, the second word that it produced was flew instead of few, which makes a lot of sense because flew is a much more probable word to come after it than few would be. And more broadly, even though the correct answer is totally ungrammatical, what GPT-4 produced, I think actually is a grammatical sentence, maybe a little bit strange. And for sure, if you look at any local chunk of just 3 or 4 words, it's a reasonable chunk that you can imagine appearing in a real sentence. So this gives some anecdotal evidence of GPT-4 really being sensitive to the probability of the sentence that it's working with. That is, if it had learned a fully abstract symbolic algorithm, which in theory is possible, this is a pretty simple task that can easily be handled with, say, a Python program, which would get 100% accuracy regardless of the sentence that you input. But it does not seem to be doing that. Instead, it's using something that, some heuristic that works well on high probability cases, but not on cases that require a stranger output. Yeah.
W phonogram? Like, is that a unit or?
Yeah, that's a really good question. I've been meaning to check that, and I don't know. My guess would be actually that few and flew are both individual tokens. Yeah, but there is also some interesting work showing that LLMs do capture the spelling of their individual tokens. Yeah, and the way you can imagine that is, yeah, just like the distribution of, flew. Yeah. Exactly. Or you get things like whether it comes after A or N, tells you whether it starts with a vowel or a consonant, things like that. Yeah.
Is it still unable to do this with multi-shot learning, like one-shot learning?
Yes, it does. Yeah. So I forget if we've done it with this exact task, but at least for some of the tasks we looked at, we did do few-shot learning. And yeah, I mean, in some cases, it helped quantitatively somewhat, but we still got the same trend of doing better on the high probability ones than the low probability ones. Yeah.
By the way, I did check; they're both real tokens.
Okay. Interesting. Yeah. So yeah. So it is very funny that it gets that then, but yeah. And so then just to make this more systematic rather than anecdotal, what we'll show here is along the x-axis is the log probability of the correct answer. Then the y-axis shows the accuracy. And across all 5 of the LLMs we look at here, GPT 3.5, GPT 4, Claude 3, Llama 3, and Gemini 1, across all of them, there's this very strong trend of much higher accuracy in high probability cases than low probability cases. So for example, for GPT-4, accuracy ranges from 2% in the lowest probability case to 83% in the highest probability case, which is an absolutely enormous range of accuracy. Okay, another example that I think I did mention this morning was counting the words in a list. So here you just ask the LLM how many words are in a list, then show it the list. And so here the x-axis shows the number that's being counted to, and the y-axis shows the accuracy of counting lists that have that length. And I think a priori, what would be natural to expect is the accuracy would just monotonically decrease as the lists get longer, but that's not what we get. Instead, this is the pattern you see, where once you get to around 30, the accuracy has cratered down to around 0%, except with these occasional huge spikes in accuracy. And if you look at where these spikes occur, they occur right at round numbers like 50, 60, 70, which makes a lot of sense because humans like round numbers. So in a training set that was mainly written by humans, you will get round numbers more frequently than non-round numbers. So for example, 60 occurs much more often than 59 or 61, and therefore it's natural for statistical models trained on human-produced text to do better on the round numbers than the less round numbers. Yeah, it's a good question. I'm not sure. It's possible that once you get there, maybe you're too close to 100 and they just really love 100. But yeah, hard to say for sure. Yeah, and I guess in general, also if you try then like run a regression trying to predict the LLM's accuracy from either the frequency of the number or the magnitude of the number, it's much better predicted by frequency. which I think is often a general property of these systems, that what makes something hard for them is not necessarily the inherent complexity of the task, but rather its frequency in its experience.
I don't understand when I write, I don't count the number of words.
Right. Yeah. So I guess this is not about, yes, when I say which numbers are more common, I'm saying just if you count how many times the number 60 appears in a corpus in any sort of context. Yeah.
Do you have any plots showing how, like the relative frequency of these numbers in the training corpus?
I don't have plots. Yeah. I think it's something like, each round number is something like 4 times more common than the ones immediately next to it. So it's more, not, astronomically more, but yeah.
Did you calculate the correlation with common word versus not uncommon word when you do the test?
So do you mean like the common versus uncommon numbers, or like whether the words in the list? Yeah. Yeah, great question. So we did run this. Yeah. So something I kind of glossed over here is under our more complete analysis, the prediction is that LLMs will be very sensitive to the probability of the output they need to produce, but not so much the probability of the input. And that is borne out here, where you get much better performance when the output is high probability than low probability. But if you do the thing you're suggesting, where the input is either a list of rare words or a list of common words, there's not much of a big difference. And even in some cases, it actually does better with the rare words than with the common words. I'm not sure why, but my best guess is that we used literally the most common words, which includes words like a and the, which might get excluded when you're counting. But yeah, haven't really tested that hypothesis. But yeah, great question.
Problems where the answers were 50 sometimes and 32.
Yeah, absolutely. Yeah, so there was this great paper by Razegi et al. Where they were looking at arithmetic problems, just simple like a plus b equals c or a times b equals c questions. And there they did find exactly this sort of thing where just accuracy had this very, very clear correlation with the frequency of the terms in the equation. And there I think they actually found it for the frequency of the input terms as well, not just the output term. Okay. So that was about the probability of the sequences that the system needs to produce. The other main type of prediction we test is that LLMs will perform better when the more general task is frequent versus when the task is rare, even when the two tasks being compared are equally complex. So an example of this is shift ciphers, which is a type of simple code in which each letter is shifted a certain number of positions forward in the alphabet. For example, with a shift of 1, hello world becomes this, because in the alphabet, the letter after H is I, the letter after E is F, etc. Or with a shift of 2, this is what you get because 2 letters after H is J, 2 letters after E is G, etc. So there are 25 possible shift ciphers. Technically, you could, because the alphabet is 26 letters, technically you could shift by 26, but then you circle all the way back to the original message, so it's not really a cipher anymore. But these 25 possible shift ciphers are not equally common. So what we did here is we took a big sample of internet text. We found every time that shift ciphers were used and counted what level of shift was used in all these cases. And you'll see that by far the most common one is a shift of 13, then in distant second place is a shift of 3, and then in third place a shift of 1. So why are those shifts the most common? Well, a shift of 13 is common because this is sometimes known as ROT13, and in certain internet communities, ROT13 is popular as a way to share information in a spoiler-free way. Like some crossword solving communities will write hints with a shift of 13, so that if you want the hint, it's easy to decipher because it's a very simple code. But if you don't want the hint, if you want to figure it out on your own, it won't be spoiled. And ROT13 is also has kind of a special place in early programming culture. Like if any of you use Vim as your text editor, it actually has a built-in macro for converting text into and out of ROT13, but not for other shift levels. Then a shift of 3 is common because Julius Caesar famously used that cipher to communicate with his generals. And so when people write about shift ciphers, they'll often mention Julius Caesar and give examples with a shift of 3 to kind of tap into that historical precedent. And then a shift of 1 is common just because it's the simplest shift cipher. So when you introduce this concept, it's natural to use that for examples, as I did just a couple slides ago. And so what I'll now show is for each shift cipher, the accuracy that LLMs get at decoding messages written with that shift level. And so here's what we get. And you'll see this enormous spike in accuracy right at a shift of 13, which recall was by far the most common one. And further, GPT-4 also shows spikes right at 3 and 1, which were the second and third most common ones, although that part isn't as consistent, presumably because the frequency wasn't as stark for those ones. But the very clear frequency difference we saw was that 13 is by far the most common one, and that's reflected very clearly in the accuracy here. Yeah. Oh, yes. So they say, here's a message written in ROT 17, which is a cipher where each letter shifted forward 17 letters in the alphabet. Yeah. So figuring out the cipher is not part of it. It's not like cracking a code. It's just, applying the algorithm of moving each letter backward. Yeah.
Did you check whether the words that you put into the cipher when you're evaluating them were actually words that appear with that cipher in the training corpus? Like, can you guarantee that these are new phrases?
Yeah, we did not, but that's a great question. Yeah, so this gets back to the thing where here all we're using is proxies for the training corpus. We don't have access to the actual one. Yeah. So hard to say, but yeah, I would love to run that analysis for sure. And here are just some specific examples to make this more concrete. So here's a case where we asked it to, decode by shifting each letter 18 positions back in the alphabet. So this is one of the cases where all the LLMs did pretty poorly, a shift of 18. So the correct answer is, I think everyone has their own path and they can make it happen. But what GPT-4 instead said was, I think, therefore I am the best, and they can come to debate. And the really interesting thing you can see here is that its output begins with, I think, therefore I am, which makes sense because this ties back into the stuff I showed earlier of LLMs being biased toward high probability strings. Well, one of the most high probability strings in English is, I think, therefore I am, because that's a very famous quotation. And so when GPT-4 doesn't really know what to say because this cipher is challenging for it, it kind of falls back to this famous quotation. Or as another example, here the correct answer was, it is sad to see that it was received from that kind of angle. But what GPT-4 instead said was, to be or not to be, that is the question, whether nobler in the mind. So another very clear example of being, gravitating toward high probability famous quotations. Okay, so everything I've shown so far has been with just standard large language models using basic prompting where you just give it a query and ask it for the answer. But a very natural question to ask is what changes if we use chain of thought? Because chain of thought, where you ask the model to solve the problem in a step-by-step fashion, that's known to really improve LLM performance on algorithmic tasks. And so specifically the question we'll be looking at here is the same one that's kind of been going throughout this talk of, is the LLM using more shallow memorization-like procedures or a more abstract reasoning-like approach? And a really nice thing about shift ciphers is that they give a pretty nice way to disentangle reasoning from memorization. Because for many tasks, it's the case that you would get a similar behavioral signature whether the model was using reasoning as opposed to memorization. Because if you're doing pure reasoning, you would suppose that the model's accuracy will just get worse as the examples get harder. Assuming pure reasoning with some sort of noise mixed in, that's what you would get. But the problem is that for many tasks, the simplest types of examples are also the most common, and therefore a memorization-like account would also show accuracy decreasing as complexity increases. So you would get the same behavioral signature for memorization versus reasoning. But for shift ciphers, the behavioral signatures are pretty different. So if they were just doing memorization, we should see accuracy that parallels the frequency of each shift level in the corpus. So you've seen this plot before. You should see a big spike in accuracy at 13, but then low accuracies everywhere else. And this is what we saw with most of the LLMs that were not using chain of thought. But then if the models are using a more systematic algorithm, we should see something more like this, where the accuracy corresponds to how many steps of computation need to be done in order to shift back. So the assumption here is that with a shift of 1, you only need 1 step of computation because you just need to shift back 1. With a shift of 7, you need 7, implicit steps of computation to shift back 7 positions. And we have this U-shaped curve, the assumption being that if the shift level is 25, you still only need 1 step to answer it because now instead of shifting back 25, you can just shift forward 1 because it works circularly. Yeah. Yeah.
So when you run 13 even, the tokenization completely changes. I checked hello world, it starts as 2 tokens, 1 for each word, becomes 6 tokens. So the model has to keep track of a history as the sentence increases in length. It has to keep track of a history. And even representation of a shallow transformer, I don't even know if it can easily represent the function which performs rock routine on a long sentence.
Yeah. Yeah, I mean, this is a great point. I think that in this particular case, it's kind of sidestepped because the form of chain of thought that we use is to first break the sentence down into individual letters. So the number of letters in a token won't be relevant because it's just always dealing with a single letter at a time.
Okay, so representation, you're guaranteeing that this chain of thought sequence exists, but
no, so this is like, so we do chain of thought with an example. We show, here's a word written in whichever shift level we use. And then we say, okay, and the way you crack this is you take one letter at a time. For each one, you shift it back that number of positions. We show like X, right arrow, V, or whatever it is for the level of shift, then show it, and then at the end concatenate them together into the, like the output letters into the final answer. Yeah. Is there another? Yeah.
You could actually just shift in one step, right? They're not that different because you just have to add that number of letters that you want to shift by. If you're actually in the letter basis, right? So
yeah.
So why is the difficulty different for different?
Yeah, so actually that is what we're having them do. So this is really implicit steps. So all that it ever writes is just like, S goes to M, like doing the whole shift in one jump. But the idea is that, S goes to R is pretty easy. That's the assumption here, at least, because that internally, when you're predicting what comes after that right arrow, you only need to look back one position in the alphabet. Yeah, so it certainly is possible that it wouldn't be any harder because it could be the case that the model has memorized, all possible shifts just as a separate lookup table. But this is the hypothesis for what would show up. Yeah. Was there another? Yeah. Yeah. And so, so these are just hypothetical curves, and then here's what we actually see. And so the interesting thing here is that these trends, this is just for 3 LLMs, show essentially a blend of the two types of curves. So we do see this big spike right at 13, but we also do see this very roughly U-shaped trend. It's certainly not very smooth, and there is some asymmetry where the left half is, looks different from the right half, but still, if you kind of squint at it, you do see some version of that U-shaped curve. So our interpretation of this is that once you add in chain of thought, the system is no longer just using this relatively shallow frequency-based approach. It still is partially doing that, which is why we still see that spike in the middle. But now it also is partially doing something that's more like genuine, albeit noisy reasoning, which is what gives us this predicted trend of that U-shaped curve. Yeah, and so this is kind of our empirical justification for that assumption. So there definitely are other ways that U-shaped curve could have looked, but the fact that we get this, I think, is best explained by supposing that sort of story. Okay, yeah, so just to wrap up here, in that first case study, the one that was based on syntax, LLMs showed impressive generalization, which is evidence for capturing syntactic structure, sentence structure in a pretty abstract way. But then in the second group of case studies about more algorithmic reasoning, now performance closely correlates with frequency or probability, which is evidence that the strategies it's using are more shallow, with the caveat that using chain of thought reasoning does help somewhat in terms of beginning to show a mixture of more shallow strategies with something more like reasoning, but still showing a blend of both strategies rather than shifting all the way over to just systematic algorithm. And so now a natural question to ask is what's different between these two types of domains? Why does the degree of abstraction seem to be different? I think a very plausible story here is that syntax is essentially what language models are trained to do. They've seen an enormous quantity of syntax. Every sentence they see has sentence structure in it. This is what they're directly optimized for. So it makes sense that they would learn this domain very robustly. Whereas algorithmic reasoning is not the direct focus of the optimization process. These types of examples are much rarer. And so it does also make sense that LLMs would not have learned reasoning or algorithmic processing as robustly. Okay, yeah, so with that, I'd like to thank my collaborators and funding sources, and thank you all.
Yeah, I think like sometimes like can you actually see like if there's like when there are both effects of memorization and what goes first, like does it, because I feel like sometimes like when you ask people a question and like in different steps and then it gives you like a wrong result and then you ask it like it's not the same as like what you got from your like last step in your response.
Yeah.
It says, oh, I made a mistake. So it's like is that kind of like when GPT has like both reasoning and memorization? It's more like leaning towards memorization because like it's an easier like texture to get.
Yeah. So I think it's a moderately complicated thing where we get several different types of patterns. So so one type of pattern we get relatively often is that in this chain of thought, each individual step is correct, but then the final answer that it gives, which should just be the concatenation of all the individual steps, that final answer is wrong. So I think you could describe that as, reasoning came first, it got that chain exactly right, but then in the final step of getting the final answer, then its priors kind of creep in a bit more and sort of distort that final answer. But there are actually, well, I guess it's the same type of thing. It does sometimes happen in the other direction too, where the intermediate chain itself has errors, but then the final answer is correct, where now it seems like it might have some ability to bypass the chain and just guess flat out what the answer should be and maybe use that to help correct mistakes. So I think it's a little hard to say in general terms, how the reasoning and memorization interplay, but there are definitely some cases where you can, see the evidence of one acting independently of the other.
So my question is that these LLMs, I think they're trained to solve system one task, right? So you're not giving them an opportunity to think. So I think the kind of task you're giving these models is more system two tasks. Right?
Yeah.
So then it really should be suited to like O1, these reasoning models. I wonder if you try O1, all these tasks to be solved.
Yeah, great question. So we did exactly that. Yeah, so I don't think I have a slide for it. But the interesting thing is that O1 does much better on these tasks than GPT-4, but the same trends continue, just so like the performance is higher across the board, but we still see similar trends of much higher accuracy on a shift of 13 than a shift of 12 or a shift of 14, and also much better performance when the answer is a high probability string than when it is a low probability string. Yes. Yeah.
Much more careful.
So we haven't tried the official full one. Yes, it was a one preview. So I mean, I think in general, the takeaway we got here is that chain of thought, whether the type of chain of thought that I showed or the more self-guided chain of thought that O1 does not solve the problem. It can ameliorate the problem. I think the thing you really need to actually solve the problem is to have integration with Python code execution, something like that. That's really the right approach for something like this. And so O1 Preview definitely did not have that. O1 Pro might have that. And if so, then I would expect it would potentially solve these issues for these tasks. But yeah, I haven't tried it yet.
Yeah, just want to ask a follow-up question to Marshall's question about the compounding factor of tokenization.
Yeah.
You're showing that with channel size, things like the model is able to do more reasoning, for the letter ciphering task, like the tokenization and the letter-wise, like operation are really not that compatible, right? I wonder how much do you think to improve tokenization when you do the channel size? Actual improvement.
Yeah, that's a great question. I don't think I have a good intuition for that. I guess maybe the right test to run here would be to go back to the non-chain of thought case and represent the message with spaces between every letter, and then ask it to decode that, but without doing a chain of thought, and then that would deconfound these factors. So we should run that, but haven't tried it.
We'll thank Tom again and take all the other questions in the break. We start the next session at 4:10, so please be back by then. We have to get out of the auditorium by 5.